Hello there, warriors. This is Miss Lemons, and we're going to go ahead and continue our conversation about heat curves, but this time we're going to apply the formulas that we learned and actually calculate the enthalpy of phase changes. Okay, so you'll see in your notes off to the left-hand side, lower left-hand corner, that there is a place for you to fill in the blanks for my step-by-step. So step one, you're going to plot your starting and your ending points on the heating curve. Then step two, you're going to determine the formulas that you need to use for each segment of the curve. Now, I didn't give you any room for this the little separate additional note here. So feel free to jot it down or squeeze it in there if you can. It's so important that you pay attention to units and signs. So positive or negative. Remember, the sign determines the direction of energy flow. And then some of our calculations will spit out joules and some of them will spit out kilojoules. So it's important that they are all the same. Step three, plug in the given values into the formulas. Just plug and chug like gas laws. And then add all of the heat terms, or Q, together and make sure that your units match. That's kilojoules and joules. You have to convert one or the other to make them match. So let's go ahead and try question number one. Okay. So if we were to heat up 45 grams of water from 20 degrees Celsius to 80 degrees Celsius, the first question asks us, what is the boiling point of this curve? What is the freezing point? Well, we already know the boiling point and the freezing point of water, but we can use this graph to help us figure out the boiling point or freezing point of any substance, because remember, every single heat curve is going to have two plateaus. And those two plateaus are just that, your boiling point and your freezing point, or your melting point. So down here, we've got our melting point, our freezing point, and that looks like it's lining up to be at 0 degrees. And then our boiling point is up here, or our condensation point at 100 degrees. So our boiling point is 100 degrees and our freezing point is 0 degrees. All right, so let's look at part B. What segments would we pass through and what direction? Okay, so what it's asking you is that if we were to heat up 45 grams of water from 20 degrees Celsius to 80 degrees Celsius. So you'll notice that I went ahead and I marked my diagram. Now, it's not required that you mark your diagram. However, I find it extremely helpful to physically draw something on a generic phase diagram or a heat curve so that I know exactly what segments I'm traveling through and what direction I'm traveling in. So this is my T initial, this is my T final. I'm only going through segment 3 and I'm moving from left to right. Now that might not make a lot of sense right now, but it does help us with our calculations. So let's take a look at question 1C. Okay, so now we're going to go ahead and using the information that was given to us here, we're going to calculate the heat energy that's been released or absorbed due to this change. Oh, excuse me. We will always be providing you with this information, so the molar heats of phase changes, you will always have that information. You just need to know how to use it. So calculate the heat energy released or absorbed due to the change. Take a look at your step-by-step. First, plot your starting and your ending points. We already did that. Then determine the formulas you need to use for each segment of the curve. Because we're only staying in segment 3, I know that I need to only use Q equals MCAT. How do I know that? Well, looking back at our graph or our labeled heat curve, you can see that segment 3, the liquid segment, we would use this formula, Q equals MCAT. You can also remember that Q equals MCAT would work because you're changing temperature, and the only other formula that you have to use is moles times delta H, and that doesn't have a change in temperature, so Q equals MCAT it is. We're going to go ahead and plug in the information that we have, so that is 45 grams times the specific heat of water, which is it's a staple. We are given that, so 4.184 joules per gram degree Celsius. That's delta T, so T final minus T initial, so 80 degrees Celsius minus 20 degrees Celsius. I went ahead and I simplified that, so it was 60 degrees Celsius. And remember, don't flip-flop these because if you end up with a negative number, that'll change the direction of heat flow. Then we're going to go ahead and multiply all those values together, and you end up with 11,296.8 joules. And we know that it's joules because we have joules per gram degrees Celsius, not kilojoules per gram degrees Celsius. So joules is our unit. Finally, we're going to go ahead and round according to the rules of sig figs. All of my numbers given to me initially have 3 sig figs, so our final answer should be 11,300 joules absorbed. Now, you can double check yourself here. You know that it should be absorbed because you calculated a positive number, and that means you're gaining energy, your energy is entering the system. But you also know you are increasing in temperature. You're moving from left to right on this graph. And so you should be increasing in energy. You should have a positive Q value. So that's why it's also important for you to remember which direction you're moving on this table.